All right, so we have an elliptic curve, a smooth curve written here in orange. The equation is x cubed plus ax squared plus bx plus c, where a, b, and c are real numbers. And we have a line y equals lambda x plus mu. Lambda and mu are also real numbers. And we want to know how they can intersect. So how can E and L intersect? So it turns out we don't have to redevelop any sort of new theory for this. We can use what we just learned about cubic polynomials. So how do you find points of intersection of a line with a curve? Well, you just set the y values to each other, equal to each other. So it's easier than, rather than taking square root of this, I'm just going to square this and set them all equal. So, if y is equal to lambda x plus mu, then y squared will be lambda x plus mu squared, which gives you lambda squared x squared plus 2 lambda mu x plus mu squared. Okay, just for the heck of it, I'm going to call this yl squared to just emphasize that this came from the line, and this other one I'm going to call ye squared just for the moment, because what I'm going to do now is I'm going to set ye squared equal to yl squared. Okay, and yet a different way of thinking about this is I could just say that the difference is 0, right? Or y squared minus yl squared is 0. Okay, so let's just write down what this ye and ye squared and yl squared are. So ye squared, that would be x cubed plus ax squared plus bx plus c minus that thing Okay, and I'm interested when this is 0. And in fact, I'm going to call this difference f of x. And look, this is actually nothing else but a cubic polynomial with real coefficients. I can even nicely rearrange these coefficients to see a different form of it. So the coefficient, this is x cubed, and there's a coefficient of x squared, which is a minus lambda squared. Oh, there's a square missing here, right? It's lambda squared x squared, lambda squared x squared, x squared plus b minus 2 lambda mu x plus c minus mu squared. All right, this is a cubic polynomial with real coefficients. All these numbers, a, b, c, and lambda and mu are real numbers, so this is a polynomial with real coefficients. So I can right away conclude something from the proposition we proved in an earlier part of this video. If a cubic polynomial with real coefficients has 2 real roots, then it has a third root also being real. What does it mean actually here? So suppose that I know that these two, the curve and the line, intersect at 2 points. I'm going to maybe write these points for the time being as p equal to xp, yp, and this q, oh sorry, yeah, doesn't matter, I could have taken that one as well, xq, yq. Okay, so these are points of intersection. So if p equal to xp, yp, and q equal to xq, yq are points of intersection, of E, and L, and in fact I may allow them to be the same point. What would that mean? Well, we'll see in a second. Let's for the moment just say they are points of intersection. Then xp and xq are real roots of f. Right? If I plug in xp into this polynomial, this thing here, I must get 0 because it gives me, it's a point of intersection of a line and the curve, so it gives me the same, so that means ye at that point is the same as yl, so that difference is actually 0. So every point of intersection gives me a root of this polynomial. So it's a cubic polynomial that has 2 real roots. So it must have a third real root. So by our proposition, f has all roots being real. All of its roots real. Our proposition, all of the roots, all 3 roots of f, counting multiplicity, are real. So what can happen with these multiplicities, right? First of all, it could be that p and q are different points. I mean, they have different x coordinates, and this polynomial would have a third root that also has a different that is different from those two. So it has 3 distinct roots, each of multiplicity 1, which will mean there is a third point of intersection, like on this picture here. What could also happen is these 2 points are actually different points, they have different x coordinates, and this polynomial therefore has a third real root. However, it's not different, it's not a different root. It could just mean that p has multiplicity 2 or q has multiplicity 2. Not both, of course, right? Because only one root in a cubic polynomial can have multiplicity 2. So it could be that we give ourselves these 2 and we don't get a third point of intersection. How can that happen? I mean, it doesn't look like it always happens. So here is a situation where it would not happen. So I'm going to now mark different points here. This is with p and q. I'm going to take my p here. I'm going to call it p prime. Okay, I'm first going to draw a line because I'm afraid if I mark the second point first, I'm not going to get the right line right. Here, q prime. I think you can believe me from the concavity of this curve that this line is not going to intersect the curve anymore. This one is sort of the point most to the left that it intersects, and that one is most to the right. These are going to diverge from each other here from that point on. So that's only 2 points of intersection, but one of them is of multiplicity 2. Do you see anything special about one of these points? Well, I kind of anticipate what's going to happen. At p prime, the line is not simply crossing the curve, it actually is tangent to it, right? It comes in above the curve and comes out above the curve as well. Why do I suspect that that's the point of multiplicity 2? Because that's what was happening with the graphs of the cubic polynomials and the x-axis. When I had a root of multiplicity 2, the x-axis was tangent to the graph at that root, and the graph didn't cross the x-axis, it came out on the same side. All right, but we actually want to confirm this by an actual calculation. So let's see. So the first case, case 1, p and q have different x coordinates. And so then 2 things can happen. A, the polynomial f can have 3 distinct roots. So L intersects E at a third point R distinct from P and Q. Or B, F either P or Q XP or XQ is a root of multiplicity 2. Then you're not going to get a third point of intersection. Then, as we'll see, the line will be tangent to E at the point whose x coordinate is a root of f with multiplicity 2. Okay, that's just case 1. The case 2 is what happens when xp is when p and q actually do not have different x coordinates. But let's first investigate this multiplicity here. So we had that polynomial f, right? So we have this polynomial f of x that was actually just given by ye squared minus yl squared. So it was x cubed plus, let's see if I remember, a minus lambda squared x squared plus b minus 2 lambda mu x plus c minus mu squared. Okay, and suppose that I have a root of this polynomial which is a double root, and I want to see what happens then. So suppose xp is a root with multiplicity 2. Okay, so then I can write this f of x as x minus xp squared, and then there's some other root. Okay, I don't really care about this other root, such some other point, x cubed. Okay, so suppose that I have this root of multiplicity 2. So what does that mean? That means that on the graph of f, I'm going to graph f here, you have these two roots, right? xp and xq. And then the graph looks like this. Goes up to x cubed and then comes down and then goes back up. So both to the left of xp and to the right of xp, f of x is negative. So both to left of xp and to the right of xp, we get that f of x is negative. Okay, but what does that mean that f of x is negative? What was f of x? It was the difference between the square of the y coordinate on the elliptic curve and the square of the y coordinate on the line. So that means that ye squared is always less than yl squared. Right? This is f. If it's negative, that means this has to be less than that. So suppose that we let's say in this situation here. So let me just erase that. Suppose that we are in this situation here, so that yp is actually negative, so that suppose ye and yl are negative in the immediate neighborhood of p. In the immediate vicinity of xp. Okay, just like on this picture here. So the point is actually below the x-axis. So what does that tell me then about these things? So it tells me that if I take, if the square of ye is less than the square of yl, then I know that the absolute value of ye is less than the absolute value of yl. Right? I don't know that. I mean, it could be, like, this one could be negative, this one could be positive. However, that's not the case, right? Because they're actually both negative. They're actually both negative in this case. So if the absolute value of y is less than the absolute value of ye is less than the absolute value of yl, and they are both negative numbers, that means that ye is actually greater than yl. Right? As this comes from them both being negative. I encourage you to do the case when they're both positive, right? And then this inequality gets flipped. So, to the left and to the right of that point, so to the left, and to the right of the point P, the curve E lies above the line L. Okay, but at point P they are the same. They intersect, which means graphically that means that I have the curve. Here I have the point P, where the graph and the curve meet, but both to the left and to the right of P, the curve actually lies above. Sorry, so not a good picture. So it's like here. The picture is going to be like this. Okay, so here's the curve, and here's the point P. And to the left and to the right of the point P, the curve lies above the line. So here the line and the curve meet. Okay? But to the left and to the right of the point, the line lies below the curve. So that means the line has to be tangent. So L is tangent to E at P. So this is how you can recognize a point of multiplicity 2. The line is tangent to the curve. So that would be a point of multiplicity 2. That wouldn't. Neither would this. Okay? There is yet another case here to consider. Let's finish this in another part.